We will start our problem with a semicircle which has the diameter of 10. Now we're going to use this semicircle to construct a rectangle in such a way so that two opposite corners of the rectangle are touching the arc and the third corner is touching the diameter of our semicircle, as you can see on the sketch. But this rectangle is placed in a special way, so that the intersection between his upper side and the arc of the semicircle is dividing the upper base into two identical segments. And also the height of this rectangle is equal in length as one of those two segments. So, the question is, can we somehow calculate the area of this red rectangle? If you guys want to try this beautiful problem out for yourself, you can pause the video as always and then come back and check the solution. Alright, so let's solve this one together. First things first, let's label all the vertices of our rectangle as ABCD. Let's label the midpoint of the line CB, which is intersection between semicircle and the rectangle, as M, and let's also label the center of our semicircle as O. Now, we know that the diameter of our semicircle is 10, which means that the radius must be 5. Now, we can take this radius and first rotate it to the point D and also to the point B. Now, we will pull one awesome magical line which connects everything, and this line is line DB. Why is this line so special? Well, first, it connects two of the radii of our semicircle, and it also represents the diagonal of our rectangle. So this line is actually a connection between our rectangle and our semicircle. And it would be quite awesome to find the length of this line. We can maybe try to do this by using the triangle DOB. And the angle at the point O really looks like the right angle. But we don't know this, we need to prove this. So let's first try to find this angle. I'm going to do this by pulling another line, which is the chord of our semicircle DM. If you take a look at our sketch, you can see that the line DC is equal in length with the line AB, since those two are the sides of the rectangle. But also the line DC is equal in length with the line CM, since this is the condition of our problem. The angle at the point C is a right angle, since ABCD is a rectangle, which means that our triangle at the top, DMC, is an isosceles right angle triangle. This is great because we know that the other two angles of this triangle are equal and the measure of those two acute angles must be 45 degrees. Now you can notice that the angles CMD and DMB are supplementary angles, which means that the angle DMB must have the value of 180 degrees minus 45, which is 135 degrees. Alright, so now let's clear our sketch and let's just leave these lines. Why? Because here you can see that DMB is actually an inscribed angle inside the circle. And we will use our famous inscribed angle theorem. This theorem states that if we inscribed an angle in any circle, this angle will always be 1/2 of the central angle that subtends from the same arc. So if I label the sketch on the right the same as sketch on the left, you can clearly see that the angle DMB is our inscribed angle. And the central angle for this angle will be the angle DOB. And this angle will be 2 times 135 degrees, which is 270-degree angle. This is awesome because we know that the overall angle at the point O is 360 degrees. So this means that the remaining angle DOB must be 360 minus 270 degrees, which is a 90-degree angle. And now let's go back to our previous sketch. Now we can clearly see that our triangle DOB is again an isosceles right-angled triangle with the side of 5. Now we can use another property of an isosceles right-angled triangle, which states that this triangle represents the half of the square. So this means that the hypotenuse of this triangle is the diagonal of the square, and we know that the diagonal of the square is equal to the side times square root of 2. So we can use this fact in our sketch, and we can conclude that the line DB must have the length of 5 square root of 2. Alright, so now let's clear the image, and let's label the height of our rectangle as A, which means that the upper two segments of the base of our rectangle must also have the lengths of A. So the overall base of our rectangle must have the length of 2A. Now let's notice another right-angled triangle DAB, and we can use the Pythagorean theorem to say that the leg DA squared plus the leg AB squared must be equal to the hypotenuse DB squared, and we can substitute our values from the sketch. Of course, we will put everything to the square and get the following. Now we can multiply this by 1 over 5 to simplify, and we will get that A squared equals 10, and we're going to leave this value as it is. Now, remember, we're looking for the area of the entire rectangle ABCD, and the area of the rectangles equals to the product of its base and the height, which in our case is 2A squared. And we're just going to substitute the value of A squared, which we got earlier, and finally we will get that this rectangle has the area of 20 squared units, and this is our solution. Well, I really hope you guys enjoyed this problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. If you found another way to solve this problem, please write it down in the comment section. And as always, until next time, see you guys and take care.